Hi, welcome. This episode is going to be about geographic maps, coordinate systems and projections of the globe. So we need to understand these in a little detail to be able to understand how to use maps in Python and indeed in many different software tools that use maps. So we'll start off in 3D. This is a geographic coordinate system, a GCS. It recognizes the Earth is a 3D globe and that we rarely use a 3D globe in mapping. Sometimes in Google Earth you do, but mostly using a 2D page to draw a map. But when you start off thinking about the world as a globe, any point on the surface of the Earth can be defined by its longitude and latitude and its altitude above sea level. We can do this against a model of the Earth as a sphere, which we have here, and you can see the angle around the axis is a longitude, and the angle up north is a latitude. These parallels, as they're called, going through the Earth, cut through the Earth and provide those lines of latitude. The vertical meridians, or ecliptics, give us the lines of longitude. So the question we have then is, how do we go from this 3D model of the Earth to 2D? Well, one way is through starting off with a datum. The Earth isn't a perfect sphere, so you need to start off by defining what shape you want to work from. And the shape most commonly used in web mapping is WGS84. It's a model of the shape of the Earth. That then lets you say, well, okay, given some longitude and latitude, this is where that is on the surface of the Earth. Google, Bing, and OpenStreetMaps all use WGS84, and the GPS systems also use WGS4 as their datum, their starting point as a model of the Earth. Essentially, you have to decide where's the centre of the Earth, how squished is it from a sphere, and therefore where do latitude and longitude end up. This is just one of a number of datum, a number of models of the Earth, so we'll see one other, but there's quite a number of these, and they're adjusted over the years as we get more accurate measurements. So now the question is, how do you go from this 3D model of the Earth with the WGS84 datum onto a 2D page? As with the model of the Earth, there are lots of ways to do this. They're all projections, so they're projecting a 3D surface to a 2D surface, and in doing that you have some compromises to make. So for example here, this is the Web Mercator projection, which is used by all web maps, and it distorts size and area, as you can see. So the size of these disks, which are all the same size on the globe, are actually different. But it retains shape. It has that nice property that wherever you look on the globe, the same shape on the same patch of Earth will be the same, even if it's a different size. It doesn't work particularly well at the North or South poles for the purposes of mapping. It does work, but it doesn't work particularly well. And therefore these tend to cut off at 85 degrees north and south, around about 85 degrees north and south of the equator. So you don't see the North and South poles. When Google and other map systems take a lat long pair, so a position of angles on the Earth's surface, and show you those on a map, they're not actually showing you where the lat and long are on the globe, which is where they're defined. They're actually converting them, they're projecting them from the 3D space of the globe to the 2D area of the map. And that's, we'll see in a second, while they report latitude and longitude, actually this Mercator projection is in a space that's 0 to 256 units in each direction, so it's a square. Another very commonly used projection is the Platecrate. This is used by Esri and ArcGIS and many GIS applications. Unfortunately, it's not compatible with Mercator directly, so when you get a map from a GIS system, it's not usually the same shape and coordinate system as a map from Google or other online sources like Leaflet. They look quite similar, but the key thing about Platecrate projection is that the areas on the map, the squares, are the same size. So 1 degree here will be 1 degree here. But this gives us distortions. It gives us distortions in area, distance and shape. Everything's distorted on these maps. But they do have this nice property that they're the same square is the same shape. And you can plot directly a latitude and longitude on here. So this is not an abstract coordinate system, this is in a lat long coordinate system. A real issue here is that a number of GIS maps are therefore incompatible with web maps. NASA also uses Platecrate as its base map projection. So anything you pull from NASA, like the Blue Marble images, will not automatically map onto a web leaflet page. You'll need to do some reprojection from Platecrate into Mercator to do that. One other thing you will certainly come across if you work in the UK is the Ordinance Survey and the British National Grid, BNG, which is a different projected coordinate system. This is different in two ways. It has a different datum. It uses OSG B36 as the datum because that's a better fit to the shape of the globe around the United Kingdom. And it uses a different projection of the 3D globe into 2D. But you will see this in all maps printed or online from the Ordnance Survey that they have these squares across the UK. You might see them referenced either by numerically or by two letters, and the letters refer to the square, and the bottom left-hand corner of the square is the measuring point that you start from. It's a system measured in meters, and you give points in meters either from the origin down here or from the start of one of the squares or sub-squares. It's worth noting the last point on the slide, you can't just easily convert from BNG to WGS8 for web maps. You need quite a complex piece of maths to do that, so either you'll need a library or the maths coded into a function for you to convert between the two accurately. Okay, so that's it for maps and map projections of the 3D globe into a 2D map space for now. We'll start to show you some of the code in Python with the CounterPy library in the next episode.